In Module 5, we're going to study more circuit analysis techniques that are considered useful. In Module 4, we looked at mesh and nodal analysis, where we looked at an entire circuit, and we could solve for all the mesh currents and all the nodal voltages and/or all the nodal voltages, depending on our choice, by solving for a system of equations. Our goal in this module is we're going to replace a portion of the circuit with a greatly simplified equivalent circuit, so we can do a detailed performance analysis on the remainder of the circuit. So we won't look at an entire circuit at one time. So for example, we've already looked at equivalent resistor networks. If we had this resistor network here on the right of our AB nodes, we could do resistor combinations because we have resistors in series and parallel. And we could find an equivalent resistance to represent this entire resistor network. And then we could look at just the current that would be required to be sourced by this power voltage source in order to drive this resistor network. So although we wouldn't be able to find out, for example, the voltage across R4 here, or the current through, this is R8, I think, we would be able to find this current IS, and we would be able to find the voltage VAB across between nodes A and B. So we've simplified the circuit, found a greatly simplified circuit, to be able to analyze just this portion on the left. The portion that we simplified, we can't find anything out about it internally. And that will carry through in the other techniques we learn in this module. So the techniques that we're going to look at are superposition, source transformation, a Thevenin equivalent network, a Norton equivalent network, and then based on that, we'll look at, what's the maximum power delivered to a load, and then we'll look at other ways we can combine resistors in the circuit, whether they're delta or Y connected. We'll call those network conversions. So again, let's take a look first. These are all these techniques are available to us because they are a consequence of linearity. We are studying linear circuit analysis. If the circuit's not linear, then we can't use these techniques. So we need to define what is a linear circuit. So the linear elements are passive elements that have a linear voltage current relationship. Or, we looked at, we even did a lab with Ohm's law, where our Ohm's law tells us that if we vary the voltage across the resistor, the current will vary also, but by that constant amount R. So we have our V is equal to IR, or similarly, what we did in lab is since we varied the voltage, we got our I was equal to V over R. And the proportionality constant was 1 over R, or the conductance. So that's a linear relationship for a passive element. If we have a dependent source, the output current or voltage of that dependent source, if it's a dependent current source, or if it's a dependent voltage source, that output voltage or current has to be proportional only to the first power of the specified current or voltage variable that's controlling it. So we could have that a voltage controlled source could be controlled by the sum of these two different currents, 3Ix plus 2Iy, because this is a linear equation. But it couldn't be equal to 2Ix squared or Ix times Iy, because that would no longer be linear. So a linear circuit then is composed entirely of independent sources. We can additionally have independent voltage or current sources, linear dependent sources, and linear passive elements. So that's our linear circuit. So as we've just defined, the response then in our linear circuit is going to be proportional to the source. So if we increase all the voltage and current sources by some constant K, then all the responses in the circuit will be increased by that same constant K. So if we look, for example, at this circuit, we can show a proof of linearity. We'll multiply, this circuit has 3 resistors and 2 sources. The 2 sources are current sources labeled 3 and 2. We'll assume it's 3 amperes and 2 amperes. So we can do a nodal analysis on this circuit. We could do our V1 minus V2 over 10 plus V1 over 10 is equal to the 3 amps flowing in at node 2, V2 minus V1 over this 10, plus V2 minus 0 over 20. That's going to be equal to this 2 amps flowing in. When we go to simplify that, we can multiply our first equation by 10, and we get 2V1 minus 1V2 is 30. We multiply our second equation through by 20, we get negative 2V1 plus 3V2 is equal to 40. And this is easy to solve the system of two equations and two unknowns. We can just add them up and we get that 2V2 is equal to 70, so V2 is equal to 35. And then we can substitute back in and get our V1. So that's easy enough to do. So what does that have to do with linearity? Well, what if we multiply each of these sources by that constant factor k? So it's any factor there, right? We multiply both of these sources by k. Well, how does it change our results? We multiply that by k. Well, we're still going to multiply through our first equation by 10, so we'll end up with 30k. Multiply our second equation through by 20. We'll end up with 2 times 20 or 20k, or 2k times 20 or 40k. And when we go through to solve these equations, we're still going to get, these two are going to cancel, and we'll get now our 2v2 is equal to 70k, that where k is our constant and v2 is just equal to 35k. So our response, our nodal voltage response, has just been multiplied by that constant k. So that's easy enough to show, and that's proof of linearity. All right, so, and we showed that here too, where we put the k in substitutes, or excuse me, in parentheses. Let's take another example at how we can use this linearity principle before we get into superposition. So what we can do here is, if we want to work with easy numbers, we can just assume an output voltage. So we want to know what this output voltage is based on this 12-volt source supplying this resistor network. So we're really asking what's the voltage across this 2 kilo ohm resistor. So let's assume it's 1 volt, because that's easy to work with, and then work backwards to determine what would then be the source voltage that would create our V out to be equal to 1 volt. And then we could use our linearity principle to calculate V out. Our V out over Vs has got to be equal to that constant K. So if we look here, we'll assume that our V2, which is V out, is equal to 1 volt. Well, then this current I2 flowing downward through this 2 kilo ohm resistor must be equal to the V2 divided by the resistance, 2 kilo ohms. So we solve for that as 0.5 milliamps. And then as we continue to work backwards, we can solve then for V1 by doing a KVL. So our V1, that's from here to ground, that's got to be equal to our 4 kilo ohms times I2, right? I2 is also, of course, has to be flowing here, right? Because this is 0 because of the open circuit. So that voltage V1 minus V2 then is just V2 over, it's just 4 kilo ohms times our I2. And then we add our V2 to that, which was V out, which is 1 volt. So we get a solution of 3 volts there. And then we can use our Ohm's law. We know what V1 is, that's 3 volts. So by Ohm's law, our I1 then must be equal to V1 over 3 kilo ohms, or 1 milliamp. And then we can finally use our KCL. IS then is equal to I1 flowing out plus I2 flowing out, but that's equal to 1.5 milliamps. So now that we have IS, we can find VS. VS, by doing a KVL around this loops, our VS is equal to IS times 2 kilo ohms plus the V1, and it's equal to 6 volts. So then we can apply our linearity principle, and V out over Vs is equal to 1 volt over 6 volts, and so our V out then is equal to 2 volts. So that's another way we can use that linearity principle. A couple of definitions that we'll be using throughout Forcing functions, in this case, we have two independent current generators. They force current into the circuit. So a forcing function could be a current source or a voltage source, independent current source or independent voltage source. And the forced responses that we're looking at, in this case, were nodal voltages, but we also looked at forced responses of currents in this circuit. So our responses are the currents and the voltages that are produced by the power being supplied by our forcing functions.